well, and also so that you can figure out how to use the chemistry that was learned in the lab to solve problems in chemistry in general. And you're going to have to do that in the post-lab exercises. So
I have an extra pen.
it's really important that you follow along, and this is the first of our Dreamscape labs, the first lab that looks like this, that you follow along and complete your notes as I'm completing them. All right, so X-ray fluorescence, enormously important and enormously useful in figuring out what elements we have in an unknown material. So let's talk about the elements of the Earth, because those are the elements likely to be found in a footprint. So here is an abbreviated periodic table. We've highlighted in this gray box the 24 most abundant elements in the universe. If we superimpose on top of that the 12 most abundant elements on the Earth's crust, we're going to find, not surprisingly, that there is a lot of overlap. Hydrogen, sodium, magnesium, potassium, calcium, even if you don't know what all the symbols mean, you can still see that we're basically identifying elements on Earth which are also those abundant in the universe: manganese, iron, aluminum, silicon, we'll find that's very important soon, phosphorus, oxygen, and so on. So we're not surprised to learn that most abundant elements in the Earth's crust are also abundant in the universe. However, just looking at this alone, it's a little bit deceptive. It tells us what elements that we have. It doesn't tell us anything about their relative abundance. And there we have a rather large difference between the universe and the Earth. So for instance, the most abundant element in the universe by far is hydrogen, followed by helium, followed by oxygen, and carbon, and then all of the other elements relatively small quantity. The most abundant element in the Earth's crust, however, is oxygen. There's actually not a lot of hydrogen in the Earth's crust. One of the reasons for that is hydrogen is a very light, volatile element, and the Earth's crust has gone through many heating cycles in the lifetime of the Earth. So some of the volatile elements have been excluded
not
from the
including
Earth's crust
noble
by now.
gases.
So oxygen is the most abundant, followed by silicon, followed by aluminum, iron, calcium, sodium, magnesium, and potassium. There is hydrogen in the crust, but there's not a lot of it compared to those somewhat heavier atoms. So if we're going to look for elements in a footprint, these are the elements we expect to see in a footprint. The abundant ones in Earth. We can divide the periodic table very roughly into two regions. Later in the course, we'll divide it into three regions, but for now, we can divide it into these two main regions, where those that we draw the box around, those are the small atoms. Those we're going to call nonmetals. And those are the atoms that tend to make molecules. The reason they make molecules is small atoms make strong single bonds. To make a strong bond, two atoms have to get close to each other, so small atoms can get close to each other, they make strong bonds. Most of the rest of the periodic table, at least as far as this simple analysis is concerned, consists of larger atoms. And because they're larger, they make weak single bonds. These are the metals. So metals don't make strong single bonds. Metals make many, many bonds to many other metal atoms. That's why they exist that way. In the periodic table, these elements in the final column here, these are the noble gases. And we're not going to talk about them very much in this lab or most of the labs that we cover this semester, because they tend to be non-reactive. So we have molecular systems mainly involved in those atoms, metallic systems mainly involved in those atoms. If we make a chemical which involves an atom from the metal group and an atom from the non-metal group, for instance, sodium and chlorine, then we tend to make an ionic material. So we have molecular materials, metal materials, and ionic materials. Now, this is a bit of an oversimplification. There are some exceptions to this rule, but this is not a bad general rule. If we make a chemical involving iron and oxygen, it will also be ionic. You don't have to know any of this. Fe2O3, it will also be ionic. And if we sort of look, in the Earth and ask what kind of materials do we generally find in the Earth, roughly 30% of the material in the Earth is metal. Actually, I'm going to say roughly 25, I think it's more accurate. Roughly 70% of the materials on Earth are ionic. That's rocks. Stuff like rocks are ionic. And only about 5% of the materials on Earth or within the Earth's crust are molecular. Water's going to be one. But we see that most of the material within the Earth's crust is ionic. So ionic materials, those are expected to be in the elements we detect by XRF in a footprint. And that's exactly what we see. If we look at the XRF of the footprint that Olive measured, we will see all of these metal elements. We'll see iron and manganese and titanium and calcium, potassium, magnesium and aluminum and so on. But when Olive sees iron or aluminum or magnesium by XRF, she's not seeing iron metal, magnesium metal, and aluminum metal. She's seeing iron in an ionic form, for example, as a chemical of oxygen, so an iron oxide. If titanium is detected by XRF, what's actually being detected is titanium dioxide. Aluminum is normally expected to be found as alumina, an aluminum oxide. And so on. Calcium, not maybe an oxide, calcium carbonate. Again, these are all ionic materials. Now, that doesn't mean that all of the calcium is present as calcium carbonate and all of the ions there in the form of Fe2O3. These are just examples of the ionic materials in the Earth. There are many. Silicon, the second most abundant element of the Earth, is present as almost always a silicon dioxide. So where's the oxygen? Well, the XRF spectrum, the horizontal axis is fluorescence energy, which is exactly the same equivalent to atomic number. And XRF is not good at detecting elements with small atomic numbers. In fact, it doesn't detect them at all. So, for instance, oxygen ought to be here in an XRF spectrum, carbon ought to be here in an XRF spectrum, but these light elements, carbon and oxygen, these are not detected. So, from here, we expect there to be lots of oxygen in the Earth's crust, and there is. There's oxygen chemically bonded to iron, and magnesium, and aluminum, silicon, and so on. It just didn't appear in the XRF spectrum, but it's definitely there in the Earth. There's a couple of exceptions. Sodium and chlorine. We already decided a chemical including a metal, sodium, and a non-metal chlorine should be ionic, Na+, Cl-. But sodium chloride is not found in the Earth, or hardly at all. Almost all of the sodium chloride is found in the oceans. So, all of these elements we expect to see in a footprint comprised of Earth, and we do. But sodium chloride is unusual. Sodium chloride is the major contributor to ocean salinity. Salinity is a measure of salt concentration in water. The reason the oceans are salty is mainly due to sodium chloride. The amount of sodium chloride in the different oceans are different. So here we have the world, right? And here is the Pacific Ocean, here is the Atlantic, here we have the Indian, the Southern, and the Arctic Oceans. And of all of the oceans, the Arctic tends to have low salinity, meaning a relatively low concentration of salt. The reason for that is because of glacial melt in the Arctic region, which generates fresh water, and also the presence of some very large rivers in Siberia that dump large amounts of fresh water into the Arctic Ocean. Parts of the world which have high salinity is the Mediterranean, the Red Sea, and so on. Those parts of the world are hot, so there's a lot of evaporation, and there's not a lot of fresh water input into those bodies of water. So we're going to be talking a lot about salinity in this lab, which is the same thing as salt concentration. And we're going to need some units for concentration. The units we're going to be using in this lab are mass concentration units, specifically, mainly in this lab, PPT. PPT stands for parts per thousand, which is simply the same as how many in 1,000, or how many what. This is a mass unit. So, for instance, how many grams in 1,000 grams. For example, let's imagine we have 38 grams of salt, sodium chloride, in 1,000 grams of water. Then that's simply equal to 38 ppT. That's the concentration of salt, sodium chloride in water. Well, that was an easy example, right? Because it's just 38 grams in 100. Let's imagine, sorry, in 1,000. Let's imagine we're not given the volume of 1,000. You know, how we're going to do this? There's an equation. We can use sort of ratios and common sense for other situations, but honestly, it's okay just to know an equation. So the equation for parts per thousand is weight of salt, in our case, in grams, divided by weight of solution in grams, multiplied by 1,000. That's simply telling you how to do a ratio. So, for example, let's imagine we have 7 grams of sodium chloride, simple table salt, in 200 grams of solution. Okay, we can use our little equation. So that's going to be 7 grams divided by 200 grams multiplied by 1,000. That's 35 ppT, 35 parts per thousand. Now, when ionic materials such as salt, sodium chloride, dissolve in water, they form solutions that conduct electricity. And it's an important property of ionic materials. Not all ionic materials dissolve in water, but when they do, they form solutions that conduct electricity. And furthermore, higher salt concentrations means higher conductivity. So in other words, if you measure the conductivity of an unknown solution, you can determine the salt concentration. And that's what you're going to do in this lab. We're going to give you a conductivity probe, so you can use this to determine the concentration of an unknown salt solution using the following equation. Concentration in units of ppT is given by conductivity BIL period times 10, and I'll explain what that is in just a second, times 0.0055, where the conductivity is in units of microsiemens per centimeter. Don't worry, there won't be a test on that. That's not the important part. The important part is this. The concentration of a solution is given by the conductivity of solution after it has been diluted by a factor of 10. The conductivity probes you're going to be given are quite sensitive, and in fact if you put one into just regular Pacific Ocean water, the concentration of salt is so high that the conductivity probe cannot measure it accurately. So all solutions that you measure today will be diluted by a factor of 10, and we'll either tell you how to do that or we'll have already done that for you. And so once the solution has been divided by a factor of 10, then we can determine its conductivity and use this equation to determine the unknown concentration in parts per thousand. And that won't mean a lot to you yet because you haven't done it yet. After you've done this process, then it will click how all this works. So how can that tell us where the arsenic came from? So we know the arsenic has sodium chloride, salt, in its footprint. Oh, I just said here. I should have said there. I've already reduced the number of suspects in the world by a factor of 2. Sorry about that. So we know that the arsonist recently stepped in salt water, almost certainly ocean water. And the question is, what is that ocean water? And by figuring that out, can we tell where this person came from? And we can do that if we know the concentration of the salt water, because we already decided that different oceans have different salinities, different salt concentrations. So we will use conductivity to determine salinity of the water the arsonist stepped in from footprint and compare to the known concentrations or conductivities of the oceans. To do this, we're going to need the volume of water in the footprint, and we're going to need the mass of salt that was in the footprint. So you will get these pieces of information today in part of your lab work. You will then use conductivity and compare with conductivities of the oceans. Okay, so what will you actually do? I'm not going to tell you in detail all the things you're going to do because we have these like pictorial representation steps of what to do, and we believe that if you follow these, this is sufficient, this is all you need to figure out how to make experiments work today. If I tell you everything you're going to do, you're going to forget it anyway. But I just want to point out some important parts as we go through. Again, not details, but important points to look for. And the first important point is you have to clean the glassware you are going to be using today. You can't assume that whoever used the glassware last left it clean. So these are the various pieces of glassware you're going to need. You should be able to find them next to your bench. You should wash each one with a small amount of the green clean detergent. Rinse thoroughly with water, rinse with DI water, and then dry using a paper towel or by shaking vigorously if you can't dry the paper towel to get as much of the water as possible out of the glassware, because you're going to be making solutions in water today and you want to measure the amount of water accurately. So if there's water already left in the glassware, that's a potential to mess things up. And then the first thing you're going to be asking is, well, how do you know how much water there would be in a footprint? Well, you don't have the actual arsonist shoe in the lab, but you have an example shoe, and you're going to figure out what the volume of water would be in that example shoe. You're going to start by taking a piece of paper towel, folding it in 3, and then folding it half again, weighing it, and then, well, I'm not going to tell you everything else that happens. The TA will help you figure out how much water there is in this example shoe. Yes, so yeah, you're going to do experiments on a shoe today, an actual shoe. I mean, why wouldn't you? This whole lab is about figuring out, you know, a person's shoe, so why wouldn't you do experiments on a shoe? The next thing you'll do is find out how much salt really is there in the ocean water. So you get a good feel for this, we're going to have you make your own ocean water, actually, more technically, seawater. We're going to have you make your own artificial Mediterranean Sea by weighing out as accurately as you can a certain way of sodium chloride into a weighing boat, as accurately as you can DI water into a 250 ml beaker, and just follow these directions and you'll get there. This will make your own Mediterranean seawater, which you will then dilute by a factor of 10, so you get diluted Mediterranean seawater that you can then do a conductivity measurement on later on. All of the samples you make today in the lab, the glassware, I want you to label them with a dry erase marker so you don't get things confused. So you want to label this with diluted med C, right? Write that in dry erase marker on the beaker so you don't lose track of what's what. The third thing you'll do today is use conductivity to determine salt concentrations, salinities of actual ocean water. First, you need to connect your conductivity probe to the graphical analysis app. You can use your own phone for this, or you can use on the iPads. You should have seen this procedure before, but if you can't remember how to do this, the procedure is given for you here. Once you get to, once you have connected, Bluetooth connected, don't press collect. You're not going to be collecting data. Just make sure you turn on meters, and the meters will give you a real-time reading of conductivity. You are provided with authentic samples of the Atlantic, Pacific, the Indian, and the Arctic Ocean, and you have your own sample of the Mediterranean seawater. You go pick these up at the TA station, apart from the Mediterranean one. You have that yourself, and then you're going to measure the conductivity of each of these samples. And you'll notice that when you measure the conductivity, here is the unit, microsiemens per centimeter. Well, there'll be a test on that. You notice that the last two digits will bounce around. So for instance, if you read 5237, 10 seconds later it's going to be 5241 or 5233. So ignore those last two numbers. So if you have 52 something, record that number as 5200. In other words, take a measurement to the nearest 100. So you'll make all those measurements, and then you'll use this equation, the one you've already written down, to convert the conductivities into concentrations of the Atlantic, the Pacific, the Indian, the Arctic, and your Mediterranean Sea. And this equation takes into account the fact that the solutions are already diluted by 10. The last thing you'll do is identify where the arsonist came from. So IT scientists have found the actual shoe that he used. We don't have it here in the lab, but they made measurements and they figured out that the actual shoe would contain 5 milliliters of water in the footprint and 4 grams of footprint material. At the TA station, you are provided with footprint material. There's enough footprint material. Otis and Olive worked hard. They collected a lot of footprint material for every group to have some. Take one of these tiny 10 ml beakers and fill it roughly a third full. That should be roughly 5 to 6 grams of footprint material. Weigh exactly as accurate as you can 4 grams of this material into a weigh boat. Add as accurately as you can 50 milliliters of DI water. Not 5, you're going to add 50 because that will already dilute the solution by a factor of 10, and this will reproduce the water that the arsonist stepped in. Stir vigorously, wait for a while until it will settle, measure the conductivity, and then use the same equation again. Use the conductivity to determine the concentration of the salt water the arsonist must have stepped in. And by comparing this with what you measured up here, you'll then know where this person came from. Everything you do today, you're going to write down in this section 3 of the package you've been given, all the notes you make, right? All the measurements you make and any notes you want to make go right here. So again, this was the example footprint, the mass of the dry paper, mass of the wet paper, the mass of water in the footprint, what's the volume of water in the footprint, the conductivities of the various oceans, convert those into cylindrical. Write all this down because you need it, and you need all these numbers to complete the lab properly. And you have to submit all this stuff at the end of the lab anyway, and then complete this table right here. After you've done all that, before you leave the lab today, everybody individually must navigate to Canvas, find this post-lab assignment 3, and submit basically the contents of this table up to Canvas and a few other things as well. This isn't hard, right? This is basically just writing down what you saw and what you learned. And again, the purpose is to make sure everybody understands what they did in the lab today and what they learned by doing the lab today. And then finally, there is another post-lab assignment, which also has to be submitted individually, not group work. The deadline for this is a week after the lab. However, we strongly suggest that you start to work on the second post-lab assignment in the lab before you leave. You can work on it with your group mates. You can ask the TAs for help. The purpose of this additional post-lab assignment is not to test you, it's to help you learn. It's to take what you've learned today in the lab and learn how to apply that to other contexts beyond just measuring the footprint of an arsonist. So what you'll find is that when you submit that assignment, you'll find that you can submit it more than once. You can submit it twice, but when you submit it, you'll find that every problem that you submit here has a detailed explanation on Canvas, and almost all of them have a video explaining how to solve that problem. So that allow you to dig into that information and submit the whole thing again. Because the purpose of this last assignment isn't to test you, it's to help you learn how to take what you've learned in the lab and use it in a different context. This one has to be done in lab. The second one, I suggest you at least start it in the lab. All right, that's what you're going to do today. You're going to be solving a crime. A lot of what's included here is included in real forensic science. XRF is used lots in real forensic science, and figuring out how to work with concentrations and measurements, critical part of forensic science. So that's all I want to tell you. Let's get going and let's enjoy this lab.
Okay, guys, there are two things that we're going to do differently compared to what I am saying into the video. First thing, we will not cleaning our glassware before we start, because yesterday I already asked the student done that for you before they left. So I think they already done a good job of cleaning stuff, so we don't need to start cleaning that again. But before you guys leave, make sure you do the same thing for the next lab. Cool? Second, when you are ready to get a footprint, it's not located here, it's located in the back to hood over there. I'll be sending there and like give you a stamp. Okay. For other materials, you have footprint material right here. You have different sample of seawater from different oceans right here for you. Have 4 types of different seawater, so one group take 4. All the dry markers, weight bolts, spatula. For all the salts in your bin, one group have a lot of salts supposed to be there. Maybe you check somewhere else. So then, quick notice, you're gonna have later. You're gonna have a beaker that have sand, mixture of sand and water. We don't want you to like dump that thing inside the jar. Try to get all the liquid part into the jar, and the solid, we already prepared a beaker here for you. Transfer the solid into this beaker. Cool? Any question before we start?
So there's no worksheet, it's just a quiz.
So the worksheet today is different compared to the normal worksheet. First, you guys will not do that as a group. That is gonna do individually. Second, is in the format of a quiz on Canvas, and that is gonna be graded automatically. And you can submit twice. The first submission, if you get the answer wrong, no, doesn't matter. They're gonna give you instruction, video explanation for you to take that and submit for the second attempt, so you can get a higher point. So the whole point of this is it's not a test. This is for you just to learn out a concept. Cool. Any other question before we start?
Yeah. So if this activity isn't about work, should we do this individually? But
You can take that as a group, but everybody has to do that on their own.
oh, okay.
Can I get a paper? Yeah. Okay.
Okay.
So we can start to solve the cram today. Let's go, guys.
Okay, so we need to get a dry paper. So we need to get and a wet paper. I'll start with the water. Yeah. Oh, is it that one? No, right?
I don't know, I was thinking.
Nah, no one else has it. I think it's that one. We need bottles. This one, right? For the salt? This one? Oh, okay. No, for the concentration part, to measure the conductivity. Oh, we don't need those? Oh, okay.
I'm sorry, my last name is Dow, sorry.
Dow.
Okay.
Oh, done.
doing.
Yeah, fold it in half and then wait, and fold it in thirds.
Okay.
Okay, guys, we start to do experiment now to put on your goggles.
Okay. Is what? Oh. You have you have that thing that you put in to measure. Did we get salt?
Yeah, it's in there.
Oh, it's right there. Okay.
You get this, now you just put the shoe on.
Wait, so what was this? What was the weight?
It's 2.79.
Yeah.
I feel like it has to be longer. This is pretty short.
So now we have to have them step on it or whatever.
You can probably start doing point one or was it point
Okay, guys, so please put the goggles and gloves before you start, okay?
Oh, gloves. Okay. Are we doing 1 decibel point? So are we rounding or? So you did 2.8? Okay.
So 10, well, 11 is the max. I did that too.
Density is 1? Yep. Okay, so now we're good to do table 2?
Yeah.
Oh, do we have to do this group number stuff? Oh yeah, we do. Because we're gonna have to take a picture of it. We'll do that after, or we can do that now. Is the due date?
I don't know.
The due date is the 27th. And it's, I don't know what lab section we are. I'm gonna just say 8 a.m. Friday.
Yeah.
Alright, sick. So now we get water.
Yeah, we do conductivity of the ocean.
So do I put water in here?
I think we just do it like in there. Just stick this in that.
Oh, I thought we stick it in here. Because we're diluting every time. I'm pretty sure. Oh, we're diluting it. Yeah, we're measuring it in this big one. In the 100 milliliter one. So it says. I don't know how much we're diluting it by.
By 10, isn't it?
Yeah, but like the first one.
Wait, I think we do this. The first one we make our own, and then
Oh, my bad. I'm looking at the different other one. Okay. Add roughly 150 milliliters of diluted water.
oh, they're already diluted. That's why we.
So do we make our own 150 milliliters of diluted water?
Why don't we make our own for the Mediterranean?
Yeah. We make our own Mediterranean.
So
So 8 grams or 0.8 grams of salt in the
no, my bad. Oh, it's 0.8?
Yeah.
Okay. So do I need to get 250 water or no, like 200 some 242 of water?
No, it's just 250.
Okay. Of water?
Yeah.
Okay.
It says 20
Oh, no, I think
milliliters.
So
I think the
oh, you add the
250 is just like how much
total.
that can have.
So
20 milliliters of the DI.
wait, what?
Hey, 20 milliliters of DI water.
That's diluted water.
That's DI.
So,
You get it from the.
oh.
It's that.
Yeah, I don't see it.
Or,
Is it maybe over there? Like our like glass?
What?
Yeah, it is.
you put it in here, and then you get 20 milliliters. Put it in with the salt.
Yeah.
So first you need to.
So we're getting 20 milliliters of water?
Yeah.
The
Okay.
DI.
DI water.
I think it's.
DI water? Okay. 20 milliliters of this.
Yeah.
Is that good? Okay. You just pour it?
So you see the weight job there?
Okay. Would that be like, well, do we measure that? You don't have like a, you just mix it like that? So that's Mediterranean. Then we add 180 milliliters?
Yeah, we have to.
Okay. Does this have? Is there? There's not a bigger one, right? So we just do this 180? Okay.
I don't know, there might be a bigger one.
I didn't see one. We could use the oh, this one? Sorry. Are you measuring the conductivity or?
I think we do it after we dilute it.
Yeah, we diluted it.
No, not this is
Oh,
like
this
the
is
water.
this is just regular water?
Yeah.
Oh, okay.
This is like
This takes like a long time. Can I just do this? We need 180? Okay. Well, it looks like we're running out. Okay.
That's the tea
That is DI water.
DI water? Not.
So here. Can we do this? Write anything down on the other chart. That would nice to write whatever we get.
Would you record in there? Would you record in there? Because those are the things recorded.
No, we just put that in there. To get the
Okay. Okay. You have a napkin? Can you grab a napkin, please? What is DI water?
I think it's just distilled water.
Okay. Okay, this is 100. So we poured. Oh. Sorry. I thought it was only 100.
I just realized.
Oh yeah, so.
Okay, so here's 100. Okay, here's 80. What else do you have to do? You just swirl it and then measure that?
So not pizza, 150. So another beacon.
Okay. I'll just fill up to 100 for now. Wait, did you measure that one? No, did you measure the conductivity?
No, we have to like put it in the valve and then put it in the.
Oh, okay. Okay.
yours, marker. If you need
Put in here. 150?
Yeah.
Is the football material just the same, right? The football material is just the same. Football material?
Putting it.
It's just the same, right? Like,
Okay. They're good. Did you swirl that one? I mean, I think you can use this.
thank you for the help.
Do I need to get more?
Okay, so I think you need 4 grams of whatever you're gonna get here first. Okay, geometry is 60. I think I'm combining last two.
I think you have to hold it,
6,900.
like, so it doesn't touch the glass. That different? Okay.
6,900.
Okay.
Are you ready? Yeah. Yeah. Oh, let's see. You know how to round it up, right? Don't forget about that.
What's diluted times 10? You know?
It was just when we like put the extra water in there. So it's already been diluted, and all these ones are like diluted too. Okay, the Atlantic is 65.
Diego, so for the conductivity times diluted time, so like, how do you calculate that? What's diluted time?
The concentration.
This. What is this?
That's diluted by a factor of 10.
So
So it's already diluted. We just get the.
so what's the mass? Is that
We
just the
don't.
mass?
We haven't done that yet. It's for the when you get the foot.
Oh.
That's the third part. Right here.
Oh, okay. No, because to find salinity?
Oh, the salinity. That's
Is that not the same thing? Is it weight divided by the weight of solution?
I think that's just the same thing. Same as concentration. But
I thought they're different.
Indian Ocean is 59.
Oh.
5900.
Yeah. No, they're different, right? Because this one's kind of. Oh. Because it's times 0.005, right?
Well, that's
I think.
Actually,
I think that's how you find the salinity.
Yeah, 'cause that's like.
So what? How do you find diluted? What's the diluted?
It's already diluted. So you just get this, and then times it by 0.00.
Okay, so that doesn't. Okay. So you don't have to worry about this at all.
Yeah, that's how you find the salinity.
Same as Indian?
Yeah.
Okay. What? I don't get it. Oh, you just divide it by 10?
Connectivity times 0.00.
5200? Okay.
Okay, so
And then multiply whatever we got, and then that would be the.
What are you guys using to stir the thing?
Stir the.
I just those are right.
That's,
There was
I
like
think
a
so,
little-
yeah. It's
Are you guys using the spoon?
yeah.
Okay.
Huh?
They were using the.
We just I feel like you just really just times it by 0.005?
Yeah, that's it. You just multiply it.
Okay. Okay, I have the calculator.
I got 35.75
Yeah.
for the first one.
Oh, it's to the nearest whole number though.
Oh,
So 36.
36.
Nearest whole number?
Yeah.
Okay, Mediterranean is 35. BPT.
32.
Arctic Ocean is 26. And Pacific and Indian are 32, you said?
Yeah.
Atlantic is what? 36?
Yeah. Wait,
I-
you got 26 for the Arctic. That isn't okay.
Is it not?
I got 29.
Yeah, I got 29.
Uh, wait, what is it? Is this how you do it?
It's 0.0055.
Oh, 55?
Yeah.
So it's 38 for the last one?
Yeah.
Oh no, it's not because I'm thinking we're done. It's just like, 'cause I know I'm gonna add water. So then, alright,
Fill the 10mm beaker.
Huh?
We need to fill the 10mm beaker with the footprint material.
Oh, do you need...
Oh,
Is that the 10 milliliter? That's 50?
Well, I think I brought it here. Oh, you already did.
Yeah, I got that.
Yeah, she already. Yeah.
Okay.
more water.
Oh, and that's it? That's all we have to do?
Yeah. And then there's like a worksheet.
No, I think that's it.
Well, there's an individual.
Oh yeah, we can do that together. I'm gonna double check our data. Did you do that? Double check this. Or maybe I can just look it online. Wait. Are we supposed to, is it not supposed to be 1,000? Are we supposed to divide it by 100? The conductivity, are we supposed to divide it by 100? I looked it up. It's in like decimals or something.
Well, I don't think so.
Okay.
I don't think so. Cause it says I mean, it gives you the formula right here. Concentration parts per thousand equals conductivity times.
Okay.
Okay.
What's the units for this? Is it just S? Is it S/M for the units? Right? CM? CM? Yeah, I think it is 1,000. You're right. It's like some weird mu and then SCM. How do you know when it's good?
For a minute.
Oh, okay. Yeah. It says for the no, I was just saying we have to take a photo of this.
Oh.
Oh, so it's probably Arctic. So 0.0055 times 4900 is 27.
Yeah.
R2.
Yeah, but not because of study, but it's
Wow. Wait, what?
Let's go, guys.
What do you mean ocean identity? Did we just both put Arctic for those?
Yeah.
Yeah.
Okay. 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 You want to double check this? I'll try to double check
Yeah,
the data.
Yeah, we can put what just so it's like we get to see the size of it.
Okay. But this one you haven't. You have one here. Oh, wait. That's what you want. But we're just looking.
She said it looks good.
You did it.
Yeah.
Yeah, that's like the big
I have to put her name before we take a picture.
Look.
The other one's just like.
I get 4 grams.
Okay. We get 950. Wait, did you double check and you said it was good?
Yeah.
Alright. Can I double check mine? 36, 32, 32. Okay, thank you. This is my name. Can you read it? This is her name.
I just put my own name. I
Oh.
don't think you have to put it on
I thought we had to, because it's a group number, but,
I think that's just for the.
I thought this is like our worksheet that we all submit, but yeah, you're right. I'm not sure.
Who's individual?
Oh, I gotta do the freaking. Do we use this? Oh yeah, we did.
They said it was part one, and that was like. Or at least for that. Like, we got time to look at it out. I don't know. Because then what would we do with this? What would be the place? Like, what would we see how much the results in the
Oh, we have to. Oh, okay. For the post lab, we have to like put our data in. Okay. What? What was the actual 4 grams of footprint material and 5 milliliters of water? The actual boot was larger, right?
Yeah.
Oh, you can only put numbers, but.
There's like a worksheet, right?
Yeah.
It's individual. But I mean, I'll probably.
Yeah, I'll try to get them too.
Yeah, probably post what I can.
Guess we just keep this. I can clean these or put them back.
I already.
Oh, thank you. Okay. I need to clean this. Is this ours? The small one? Oh, okay. I didn't grab it, that's why, so.
No, they have it in there.
Okay. Alright, thank you. Appreciate y'all.
I really just got it now. Still a little close. But we're actually supposed to get that. Maybe that's not good. Does that mean Sam does? So, I mean, the water's a different color. I know it makes sense. It's like,
It's not really a worksheet. It's like a quiz.
What's up?
It's a quiz instead of a worksheet.
Yeah.
Yeah.
I still gotta do my Alex. So. Okay.
Did you have my backpack, please? Thank you. We solved what ocean he stepped in.